Welcome to the Deep Dive, your shortcut to becoming thoroughly informed. We take dense sources, listener sources often, and pull out the key stuff.
Yep, making complex topics accessible.
Exactly. And today we're diving into a really interesting research paper a listener sent us. Deep Speech 2, End-to-End Speech Recognition in English and Mandarin. It's from Baidu Research.
Yes, deep speech too. That was a big one. It really represented a shift.
How so? What's the core idea?
Well, the main thing was moving away from those older, really complicated speech recognition systems. The ones with loads of different engineered parts.
Right, like separate acoustic models, language models, all that.
Exactly. They aim to replace all of that complexity with just one single end-to-end deep learning model.
And the kicker is, it was designed for both English and Mandarin.
Precisely. Which is pretty ambitious when you think about how incredibly different those languages are. Structurally, phonetically, everything.
Totally. So, okay, our mission for this deep dive is to unpack the key advancements in this Deep Speech 2 system. Why was it such a leap forward?
We want to understand the breakthroughs, yeah. And there are some surprising bits in there about performance, like getting close to human accuracy, and also how they actually deployed it.
Okay, sounds good. Let's start with the basics then. What was wrong with the old way of doing speech recognition?
Yeah.
The pre-Deep Speech 2 era?
Well, like I said, it was intricate, super intricate. Think of it like a complex pipeline, maybe.
Okay.
You had distinct stages. First, you'd extract features from the raw audio, like turning sound waves into numbers the computer can work with.
Got it, like spectrograms?
Yeah, things like that. Then you'd have an acoustic model trying to map those features to sounds, like phonemes. Then a pronunciation model to figure out how sounds form words. Then a language model to string words together sensibly.
Wow, okay. That sounds like a lot of moving parts.
Yeah.
And each one probably needed expert tuning.
Exactly. Each component often required deep domain knowledge, phonetics, linguistics, signal processing, and getting them all to work together smoothly, especially across different languages or noisy conditions, it was tough.
I can imagine. And probably didn't generalize well. Like if you built a great system for English, adapting it to Mandarin would be a nightmare.
Pretty much. You'd have to rebuild or heavily retune large parts of that pipeline. It wasn't flexible. It's so different from how humans learn, right?
Yeah, we just sort of pick up languages. We don't have separate modules we swap out.
Right. We learn robustly, handle accents, noise, new words. The goal of Deep Speech 2 was really to build a system that acted more like that, a single adaptable learner.
Okay, so ditch the complex pipeline, bring in one big neural network. That's the end-to-end deep learning approach.
That's the core idea. Just map the input speech directly to the output text. Simple concept, but making it work required nailing three key things.
Which were?
1, the right kind of neural network architecture. 2, huge amounts of labeled training data. And 3, serious computational horsepower to actually train these massive models.
Architecture, data, and compute. Yeah. The holy trinity of deep learning, basically.
We got it.
All right, let's break those down. First, the model architecture. What were the innovations there?
They went deep, really deep for the time, up to 11 layers in some models.
11 layers.
And these weren't just simple layers. They used bidirectional recurrent layers, LSTMs or RNNs, which can look at the audio both forwards and backwards in time, helps capture context.
Right, so it doesn't just predict based on what came before, but also what comes after.
Exactly. Gives it a much richer understanding. They also used convolutional layers, especially early on, which are good at finding patterns in the raw audio input.
But training something 11 layers deep, isn't that notoriously difficult? Vanishing gradients and all that?
It definitely can be. And that's where batch normalization came in, specifically adapted for recurrent neural networks.
Batch norm. I usually think of that for speeding up training in computer vision.
That was the common wisdom, yeah. It helps stabilize training, lets you use higher learning rates. But the Deep Speech 2 team found something else, something kind of surprising for these really deep RNNs.
What was that?
They found it didn't just speed things up, it actually significantly improved the generalization error. The final accuracy on unseen data got much better, especially on their deepest models. Up to a 12% relative improvement in word error rate, which is huge.
Wow, okay. So it made the model fundamentally better, not just faster to train. How did they apply it to RNNs? Isn't that tricky?
It is. They used a specific technique they called sequence-wise normalization. Instead of normalizing across a mini batch at each time step, they calculated the mean and variance for each neuron across the entire time sequence for all the examples in the batch.
Okay, so normalizing over time within the batch.
Right. seemed to work well for stabilizing these deep recurrent nets, but it did create a bit of a headache for deployment.
How so? Because you don't usually have big batches during inference. You're often just processing one utterance at a time.
Exactly. Batch norm relies on those batch statistics. So for inference on a single utterance, you don't have a batch.
So what do they do?
Clever workaround. During training, they calculated and stored running averages of the mean and variance for each neuron. Then, at inference time, they just used those stored averages to normalize the activations for the single utterance.
Ah, makes sense. Use the training time stats as a proxy. Smart. Any other training tricks? You mentioned sortigrad.
Yeah, sortigrad, it's a curriculum learning strategy. The idea is simple. In the very first epoch of training, you feed the network training examples sorted by length, starting with the shortest utterances and gradually moving to the longest ones.
Huh. Why would you do that? Start easy and get harder.
Kind of. Their reasoning was based on the loss function they used, CTC connectionist temporal classification. Longer utterances tend to have higher CTC loss values initially, and this can cause numerical instability, like exploding gradients, especially early in training when the network is still kind of random.
Okay, so starting short avoids those big initial loss spikes and helps stabilize things.
That was the idea, and it worked. It particularly helped networks without batch norm, making them much more stable. But interestingly, they found it still gave some benefit even with batch norm. Maybe helps the network tune in more carefully early on?
Interesting. Like training wheels for the network.
Pretty much.
Now, they also looked at different types of recurrent units, right?
Yeah.
Simple RNNs versus GRUs.
They did. They compared basic RNNs with gated recurrent units, or GRUs, which are a bit like LSTMs but simpler.
Oh, what was the verdict?
Initially, they found that for a fixed number of parameters, GRUs generally gave slightly better word error rates, which kind of makes sense, as GRUs have gating mechanisms designed to handle long-range dependencies better than simple RNNs.
Okay, so GRUs win.
Not so fast. In later experiments, when they focused on a fixed computational budget and scaled up the model size, the simple RNNs actually started to slightly outperform the GRUs.
Really? Why would that be?
It suggests that while GRUs might be more parameter efficient, simple RNNs might scale better. They benefit more from just having more neurons and parameters, even if each individual neuron is simpler. So for their biggest, best models, they actually ended up using simple RNNs.
Fascinating trade-off. Okay, what about the early layers? Frequency convolutions.
Right, so standard convolutions in speech often just operate along the time axis, but they experimented with 2D convolutions operating across both time and frequency in the initial layers right after the spectrogram input.
Why frequency? What does that capture?
The idea is that variations across frequency bins can capture speaker-specific characteristics, like the timbre of their voice or maybe how formants shift. It gives the network invariance to some types of spectral variation.
So that it helps handle different speakers better.
That's the theory. And it seemed to work really well, especially on noisy data. They reported a huge weir reduction, like almost 24% on a noisy test set, just by switching from 1D to these 2D frequency convolutions.
Wow, that's substantial. Okay, speed matters too. They used striding.
Yep. Striding in convolutional layers is basically skipping steps. Instead of sliding the filter one step at a time, you jump maybe 2 or 3 steps. It reduces the length of the sequence passed to the deeper recurrent layers, which speeds up computation quite a bit.
Makes sense. But doesn't that risk losing information, especially if the thing you're trying to predict happens quickly?
It can, yeah. And they hit a particular problem with English, because English tends to have a lot of characters per second compared to, say, Mandarin. If they used too much striding, the output sequence from the convolutional layers would become shorter than the actual sequence of characters they needed to predict. The CTC loss function can't handle that.
Ah, okay. So the output sequence was too compressed. How did they solve that?
Really clever trick. Instead of having the network predict individual characters like key EE, they changed the output targets to be non-overlapping bigrams pairs of characters.
Like predicting V and then E plus space as single units.
Exactly. By predicting 2 characters at a time, they effectively halved the length of the target sequence. This meant they could use more aggressive striding in the convolutional layers to speed things up without making the output sequence too short for the target label sequence.
That is neat. Solves the impression problem.
Yeah.
Okay, one more architecture piece. Row convolution and unidirectional models. Why was this important?
This was crucial for deployment, for real-time use. Those bidirectional RNNs we talked about. Great for accuracy, but they need the whole utterance before they can start transcribing. They have to look ahead.
Right. Not good for a voice assistant where you want an immediate response.
Exactly. For low latency applications, you need a unidirectional model that processes the audio strictly from left to right, making predictions as the audio comes in.
But don't unidirectional models usually perform worse because they lack that future context?
They often do, yes. That's where row convolution came in. It's a special type of convolutional layer designed for unidirectional models that allows the network to incorporate a small, fixed amount of future context.
A peek into the future, but just a little bit.
Just a little bit, yeah. At each time step, it looks not just at the current features, but also at features from a few steps ahead, applying a 1D convolution across that narrow time window for each frequency channel independently.
Okay, so it gets a tiny bit of look ahead without needing the whole utterance. Did it work?
It worked surprisingly well, especially for Mandarin. They found their unidirectional models with row convolution achieved performance very close to their best bidirectional models. That was a key enabler for low latency deployment.
That's huge for making this practical. Okay, so that covers the architecture innovations. Let's talk data. You said massive amount.
Oh, yeah. For English, they ended up with 11,940 hours. For Mandarin, 9,400 hours.
That's staggering. Where does that much labeled audio even come from?
A mix of sources. Public datasets like LibreSpeech, audiobooks, WSJ, Read News, Switchboard, phone conversations, but also, crucially, very large internal Baidu datasets. Some of this internal data was apparently long recordings with pretty noisy transcriptions.
Noisy transcriptions. How do you train on that? Garbage in, garbage out.
Right, you need clean labels. So they developed a whole pipeline to clean it up. First, they used an older speech model to force align the noisy text to the long audio.
To figure out roughly where the words were?
Yeah. Then they segmented the long audio into shorter clips based on silences detected by the aligner, and making sure silences aligned with word breaks for English. The final really important step was filtering out bad segments.
How'd they filter?
They took a sample, had humans carefully transcribe it to create a ground truth set. Then they trained a simple classifier to predict whether a segment produced by their pipeline was likely to be accurate or not based on features from the alignment process. They used that classifier to discard potentially bad examples.
Wow, that's a serious data cleaning operation in itself.
Absolutely. And they didn't stop there. They also used data augmentation.
Adding noise.
Yep. They took about 40% of their training utterances and mixed in background noise. They created this noise by just mixing together thousands of hours of random audio clips, not speech, just ambient sounds.
To make the model more robust to real-world conditions.
Exactly. Train in noise, perform better in noise.
So all this data, did it follow the deep learning rule of more data is better?
Definitely. They showed a clear power law relationship. As they increased the training data size, the word error rate kept dropping. Roughly every 10x increase in data gave about a 40% relative reduction in wear.
Consistent gains. So data was king. But you also mentioned compute. Training on 12,000 hours of audio must take forever.
On a single GPU, weeks, maybe longer. It was computationally immense. So they relied heavily on high-performance computing, or HPC.
Meaning lots of GPUs working together.
Yeah. They built a system to train a single model using clusters of 8 or even 16 GPUs in parallel. They mentioned a 7x speed up over their previous system, thanks to these HPC techniques.
How do they manage that parallel training? Asynchronous updates.
No, they actually use synchronous stochastic gradient descent, SGD. All GPUs process a batch, calculate gradients, then average those gradients across all GPUs before updating the model.
Why synchronous? Isn't asynchronous sometimes faster?
It can be, but synchronous SGD is often easier to debug and tune, and they found that for the same number of GPUs, it actually converged faster for them. They really focused on making the synchronous updates super efficient.
How they optimize it?
Several ways. They wrote a highly optimized version of the CTC loss function that ran fast on the GPU, saving significant time each epoch, like 95 minutes for English training runs.
Okay, faster loss calculation.
They also implemented a custom memory allocator for the GPUs. Apparently, the standard OS memory allocation was becoming a bottleneck with the huge activations in these deep networks. Their custom allocator avoided that overhead.
Dealing with memory management directly.
Right. And crucially, they optimized the communication between the GPUs. That gradient averaging step in synchronous SGD requires an all-reduce operation. They wrote their own highly optimized all-reduce implementation that was much faster than standard libraries like OpenMPI, especially for GPUs within the same machine.
So custom code for everything. Loss, memory, communication.
Yeah.
Real engineering effort.
Totally. It brought training times down from potential weeks to just days, enabling them to iterate much faster.
Okay, model, data, compute. But speech isn't just sounds, it's language. How did language models fit in? I thought the RNN was learning language implicitly.
It does learn a powerful implicit language model, especially the deeper networks. But they found that explicitly adding an external language model trained separately on vast amounts of text data still gave a significant accuracy boost.
So combining the acoustic predictions with linguistic probabilities.
Exactly. For English, they used a standard n-gram language model, specifically a Nessernay-smoothed 5-gram model trained on the huge Common Crawl web text corpus.
And for Mandarin.
A similar idea, but character-based. A Nessernay-smoothed 5-gram character-level model trained on a large internal Baidu text corpus.
How do you combine the RNN output with the LM probabilities during decoding?
During the beam search decoding process, the score for a potential transcription is a weighted combination of the log probability from the Deep Speech 2 network, the CTC output, and the log probability from the external endogram language model. They also added a term to penalize sequence length, acting like a word character insertion penalty.
And those weights are tuned.
Yeah, tuned on a separate development set to optimize the final where or CER.
Did it help a lot?
Yes, quite a bit. Adding the LM significantly reduced error rates for both languages. Interestingly, though, the relative improvement from the LM decreased as the Deep Speech 2 network got deeper.
Suggesting the deeper networks were indeed learning a better internal language model.
Precisely. The RNN was capturing more and more of the linguistic structure itself.
And you mentioned the LM helped more in English than Mandarin.
Relatively speaking, yes. Their hypothesis was that because English characters represent smaller units of information than Chinese characters, which are often closer to syllables or morphemes, the character-level RNN output for Mandarin was already quite informative linguistically. The external LM had less room to improve things compared to English, where predicting the next character is less constrained by language structure alone.
Makes sense. Okay, so we focused a lot on English. How easy was it to adapt this whole system to Mandarin?
That was one of the highlights. It adapted remarkably easily. The core architecture remained largely the same.
Really? No need for tone modeling or anything specific to Chinese phonetics?
Nope. The beauty of the end-to-end approach is that the network learns those features directly from the data. The main change was simply making the output layer much larger, around 6,000 units, to cover thousands of common Chinese characters, plus the Roman alphabet and punctuation.
So it directly outputs characters. No intermediate pinyin or anything?
Direct character output. This completely bypasses the need for a traditional pronunciation model, which is often a complex language-specific component.
That's a huge simplification.
It is. They used the character-level LM we discussed, a character insertion penalty, and found they could use a slightly smaller beam width during decoding for Mandarin. But the architectural improvements like batch norm, deeper networks, etc., generally showed the same positive trends for Mandarin as for English.
Really underscores the power and flexibility of the approach.
Yeah.
Okay, the moment of truth. How did it stack up against humans?
This is where it gets really impressive. On several standard English test sets involving clean, read speech like subsets of the Wall Street Journal corpus and Liber speech, Deep Speech 2 actually performed better than human transcribers.
Better than humans. On RID speed.
On some specific benchmarks, yes. On others, it was very close, definitely competitive.
Okay, that's a milestone. What about harder stuff? Accents, noise.
For accented English speech, using the VoxForge dataset, it significantly improved over their previous system, but was still generally behind human performance for most accents. Indian English was an exception where it got quite close.
Still a gap there for most accents. And noise.
Similar story with noise using the CAKM challenge data. Big improvement over Deep Speech 1, but still a noticeable gap compared to humans, especially in really challenging, realistic, noisy conditions. Humans are still very good at picking speech out of complex background sounds.
Okay, so superhuman on clean read speech, catching up on accents and noise. What about Mandarin performance versus humans?
Even more striking results there, actually. On one test using short voice search style queries, their best Mandarin system outperformed a team of 5 human labelers.
Outperformed a team. Wow.
And on another, larger test set of mixed utterances, the system was significantly better than a single dedicated human transcriber.
That's incredible. So in some fairly common scenarios, especially for Mandarin, it was already surpassing human capabilities back then,
It certainly seems so based on their results.
which naturally leads to deployment. If it's this good, how do you get it working in a real product? What were the hurdles?
Several big ones. First, latency. Those best performing bidirectional models need the whole utterance, not good for real time. Second, computational cost. Beam search with a large vocabulary like Mandarin characters and a language model is expensive. Third, some techniques like their original audio normalization also needed the whole utterance.
So the best research models weren't directly deployable for low latency use cases.
Pretty much. They had to make some smart trade-offs in engineering choices.
How did they tackle latency and the bidirectional issue?
They focused on deploying unidirectional models, using those row convolution layers we talked about to claw back some of the performance loss by not looking ahead. For the normalization, they switched to using running statistics calculated from the training set so they could normalize audio chunks as they arrived.
Okay, unidirectional models with row conv. What about the compute cost of decoding?
Two key things there. One was batch dispatch. This was a server-side scheduler. Instead of processing each user request individually as it arrived, it would cleverly group incoming requests together into batches to feed the GPU more efficiently.
Ah, batching requests on the server.
Exactly. Bigger batches mean better GPU utilization, but potentially higher latency for the user waiting for the batch to fill. They use an eager batching approach to try and minimize that user wait time while still getting good throughput.
A balancing act between efficiency and responsiveness.
Always. They showed pretty good latency figures, like median response times under a few hundred milliseconds, even with many concurrent users.
What else for optimization?
They use half-precision floating point numbers, FP16, instead of the usual 32-bit floats. Halves the memory footprint and bandwidth needed with minimal accuracy loss. They also wrote custom matrix multiplication kernels optimized for the smaller batch sizes typical in online serving, beating standard libraries.
Squeezing out performance everywhere.
And for Mandarin specifically, with its huge character set, they used a heuristic during beam search. Instead of considering all 6,000 possible characters at each step, they only considered the top n most probable ones, where n was maybe 100 or 200.
Pruning the search space aggressively. Did that hurt accuracy much?
Apparently not much. It gave a big speed up with only a small hit to the character error rate.
So after all these optimizations and trade-offs for deployment, how did the final deployed system compare to the best research system?
Pretty well, actually. They reported about a 5% relative increase in character error rate for Mandarin between their best offline bidirectional model and the deployed unidirectional system, which is quite reasonable for the gains in latency and efficiency.
Yeah, that seems like a fair trade. It shows they can translate the research gains into a practical, usable system.
Definitely. The deployed Mandarin system used those forward-only layers and row convolution, proving the viability of that approach.
Okay, what an amazing journey. From tangled pipelines to end-to-end learning, hitting human parity, and then deploying it at scale. Let's try and wrap this up. What are the big takeaways from Deep Speech 2?
I think the main takeaway is just the sheer power and adaptability of the end-to-end deep learning approach for speech. Showing it could work so well for languages as different as English and Mandarin with basically the same core architecture was huge.
Right, the generality is key.
And it demonstrated that with enough data, the right kind of deep architecture and serious computational muscle combined with clever optimization, you could reach and sometimes exceed human performance on certain tasks.
And critically, they showed it wasn't just a lab experiment. They engineered solutions to deploy these complex models efficiently in the real world.
Exactly. It proved the feasibility of large-scale, low-latency deep learning for speech.
It really highlights that combo of data, models, and optimized compute.
Couldn't have happened without all three firing on all cylinders. It really set the stage for much of the progress we've seen since.
Absolutely, a landmark paper.
Yeah.
So, reflecting on this work from back in 2015, it really makes you think they achieved so much with the tools and scale available then. It leaves us with a final thought, perhaps.
Yeah.
Given these kinds of rapid gains driven by these general deep learning methods, how close are we now, or how imminent is, a single system that can truly outperform humans across most real-world speech scenarios. Not just clean speech, but noisy cafes, heavy accents, mumbled conversations.
That's the billion-dollar question, isn't it? What are those remaining hurdles? Is it just more data and scale, or do we need fundamentally new architectural breakthroughs or learning paradigms to really conquer the full complexity of human conversational speech in the wild?
Definitely something to ponder. What breakthroughs are still needed? Thanks for joining us on this deep dive.